Hello everyone. In this lecture we're going to be looking at a new data structure known as a binary search tree. So far we've worked primarily with linked lists. We made a linked implementation, or at least we examined a linked implementation of a stack, and we also examined a linked implementation of a queue. And in last module's lab we were working with the implementation of a deck, which of course is a hybrid data structure, sort of like a cross between a stack and a queue. And in this set of slides, we're looking at binary search trees. This is the first part on binary search trees, more to come. However, we review some of the basic methods that a binary search tree should support. And we also look at the way one can depict a binary search tree on paper in diagrammatic form. So here in this slide, we're looking at models of an example binary search tree. There's a couple here. Over at the left, you can see the root is 6. The leaves are 2, 5, and 8. And the height is 2. The root is always regarded at level 0. And then this second layer of nodes is at depth of 1. And the leaves are at depth of 2. And over here at the right, there's another example of a binary search tree. And you can see in both the diagram here at the left and the diagram here at the right that we're basically talking about the same keys. And I think some of you might still be wondering about exactly what a key is. A key is essentially a non-zero natural number. So that's like the integers, 1, 2, 3, 4, all the way up to the maximum value that an integer can assume in the computer language that one is utilizing. Another thing about these keys is that they're unique. That's kind of what the term key means anyway, but we're not reusing keys. But I think you'll find in some of the examples in the text there is a possibility to support duplicate keys. However, in the work that we do in this class, we're always going to be assuming that the keys we're using are non-zero natural numbers which are unique. So there's I guess, sort of like a fundamental property of binary search trees. Some people call this an invariant, which is a condition that's always true. And the condition is that if we let X be a node in a binary search tree, and we designate Y as a node in the left subtree of X, then all the keys we encounter in the left subtree of X are going to be less than or equal to the key in the parent. Thinking about binary search trees as they become large, it is possible to designate what are called subtrees. And the same rule that holds here for the entire binary search tree also holds for subtrees that occur in the binary search tree. And if Y is a node in the right subtree of X, then all the keys in the right subtree are either going to be greater than or equal to the key in the root. And this invariant, or this property, makes it possible to build some pretty sophisticated methods to perform, the sorts of operations that, you probably want to be able to perform regardless of which data structure, one is implementing. So in this example, we're making the assumption that, in fact, we would not just have a key in each node, we'd also have satellite data. which is data that goes along with the key. And then with a little bit of creativity, it isn't difficult to see how one could relatively easily implement a simple relational database using a binary search tree as the basis. And so here we have the node class to support a binary search tree. This is a little different than the node we were working with previously when we examined stacks, queues, and linked lists. In this node, we have a left child, we have a right child, and we also have a parent reference. And this parent reference always points up to the given node's parent. In the event we're talking about the root does not have a parent, so we would set p equal to the null in the event that we were creating a new root. And you can see in this standard constructor that we're just initializing left, right, and p to null. And then in our parameterized constructor, we're initializing left, right, and p. And one thing you should notice here is the use of this. And this helps us distinguish the parameter called p from the class attribute p. So this .p is actually the class attribute of p. And what we're doing is we're setting the class attribute to the node reference that's passed in to this parameterized constructor. And here we have a simple in-order tree walk. This is a method that makes sense to implement because typically when one is working with binary search trees, there really should be a way to display the keys in ascending order. And this in-order tree walk does just that. You'll notice we go all the way to the left, and then we print the key in that node, and then we go all the way to the right. However, one thing to keep in mind here is this method, in-order tree walk, is a recursive method. And you can see we have two recursive calls. The first is to in-order tree walk with x.left as the argument, and the second is the call to in-order tree walk with x.right as the argument. And then in between, we're printing the key. So what this will in effect do is print the keys in the binary search tree in ascending order. And here's an example of a binary search tree. This one's filled out a little bit compared to the two examples we just looked at previously. You can see that the invariant holds. That is, just by inspection, you can see all the keys in the left subtree are less than 15, and all the keys in the right subtree are greater than 15. And so, if we want to search for a given key, if we start at the root, we should proceed till we encounter the key or we encounter null. If we encounter the key, we found it, we can report the key was found. We could even return a reference to the node in which the key is located. And then what we can also do is if we encounter null before we encounter the key, then we know the key does not occur in the binary search tree, and we can then report that the key that we searched for was not found. And here's the tree search method. You can see we're passing in a node reference x, which initially would be root, and also k, which is our key, which is our integer value. And in tree search, you can see we have two parameters, x and k. And we're checking to see if x is equal to null or if k is equal to key. And if that's the case, we've either looked and not found the key, or we've looked and we found the key, in which case we can return x. And if the key we're looking for is less than the key of x, then we know that if the key occurs in the binary search tree, that it'll be in the left subtree of x, and that's when we call tree search recursively with x.left as our first argument, and the key k is the second argument. And then the only other possibility is if k is greater than or equal to the key that we're looking for, in which case we know if the key occurs that it has to be in the right subtree, and that's what we do down here in the else. We call tree search, and we pass in x.right as the first argument to tree search, and k, or the key that we're looking for, as the second argument. And then eventually we'll get to this base case, which occurs first in this first branch here. And the base case is if either x is equal to null or k is equal to the key in x, we're simply returning x. And with a little bit of work, it isn't difficult to show in a simple sort of mathematical way why this tree search method works. And again, I just want to emphasize the importance of the property of binary search trees, which simply states that all the keys in the left subtree are less than or equal to the key in the root, and all the keys in the right subtree are going to be greater than or equal to the key in the root. And we can also implement search in using a loop, and this is called an iterative tree search method. And we're doing pretty well the same thing. The condition for this loop is while x is not equal to null and k is not equal to the key of x, we're looping, and we're checking to see, we're comparing the key we're looking for with the key in x, and if the key we're looking for is less than the key in x, we continue the loop in the left subtree of x. Otherwise, we continue the search in the right subtree of x. And again, it's the property of binary search trees, what we've been calling an invariant, that makes this algorithm possible. We could also build a method to determine the minimum in a given binary search tree. So we start with x, which is our reference to root, and then for as long as we can go to the left until the left child of our node x becomes null, we're simply branching to the left. And by doing this, we're basically updating x, which is a reference to a node object. We're updating that until the node's left child is equal to null. And when that point occurs, we know we've gone and located the leftmost node in the binary search tree, and that is where the minimum key will always be located. We can also build a tree maximum method, and this works in a similar way to tree minimum. However, the difference here is we're identifying the maximum key in the binary search tree. We're passing in our reference to x, and for as long as the right child of x is not equal to null, we're setting x to x.right. When this while loop exits, x.right will be equal to null, and x will contain the maximum key in the binary search tree. And you can see here we're returning a reference to x. And this might not always be such a good idea to return references to nodes in a binary search tree. It might be better just to return the key instead of the reference to the node. in the binary search tree containing the maximum key. And this method, tree successor, essentially locates the successor to a given node in a binary search tree. So if the right child of X is not equal to null, that is, if there is a right subtree, we're simply putting in a call to tree minimum in the right subtree of X. And this will effectively determine the successor to the node X. And if this Boolean expression attached to this if evaluates to true, or I'm sorry, if it evaluates to false, we know that the right subtree is empty. There is no right subtree. And then we proceed by setting this local node reference y equal to the parent of X. And for as long as y is not equal to null and X is the right child of y, we're updating X and we're updating y, and we're proceeding in this while loop until one of these conditions becomes false. So if y is equal to null, that'll cause the while loop to exit. If X is not equal to y.right, then the while loop will also exit. And then when the while loop does exit, we simply return y, and y again is the key that follows the key contained in the node that's passed into this method, tree successor, which is this parameter here, X. And this method is probably the most sophisticated method we've looked at so far regarding binary search trees. However, we're going to get into some additional methods in the next lecture on binary search trees.